Hi guys, Sajjad Hussain again with the new video. Today we are going to discuss the response of a damped single degree of freedom system with harmonic loading. As you can see from this figure on the right hand side, what we have considered over here. And let me tell you that this is my lecture number 5, and this is my lecture number 5. This is the date and time, and what we have considered over here, that there is a body of mass m which is resting on a frictionless table or frictionless surface, and a spring constant K is attached to this body, and a damper with damping coefficient C is attached to this body. There is a force F naught sine omega bar T which is acting on the right hand side, and because of that there is a displacement of U on right hand side. So here is the free body diagram. As you can see, mu double dot is the inertial force which is acting on the left hand side. Ku is the spring force which is acting on the left hand side, and the force in the damper is Cu dot which is acting on the left hand side. Here our assumption was, as you remember in my previous lecture, that we assumed that this damping is proportional to the velocity, and this external force is acting over here. So we can write easily the equation for this motion. All the left hand forces are here, mu double dot plus C dot U plus Ku. So left hand forces are equal to right hand forces, which is F dot sine omega bar T. Let it be our equation number 1. This is the equation of this whole system. Now, you may notice that this is a non-homogeneous differential equation. So for such a non-homogeneous differential equation, as we discussed last time, that there may be two solutions. One is called a complementary solution. This is the complementary solution, and this is called particular solution. If you recall, complementary solution was this solution when we considered that there is no external force. That means external force was absent. In that case, there was only one solution, that is the complementary solution. Particular solution means when the force is acting on the system. So our total solution will be U will be equals to a sum of UCT plus UPT. That will be the complete solution. So we can see here the complete solution, that will be equals to U of T. This will be equals to U of CT plus U of PT. Let us number these equations. Our first equation is this. Let the complementary solution, this is the equation number 2. Particular solution, let this equation number 3, and let it be equation number 4. That is the final solution. And from our previous definitions, we remember that omega was the undamped frequencies of the system, which was equal to under root k over m. Omega d is the damped frequency, which is equals to omega into 1 minus xc squared, and xc is defined as C over CR, where CR is the critical damping, which is equals to under root 2 times under root k into m. If you remember, we discussed 3 different cases, like let me clear this. Okay, so if you remember, there were 3 cases. Number 1, the system may be an underdamped system. Or it may be critically damped system, or it may be an over damped system. And if you remember from my previous discussion, that over damping, not a significant case, critical damping, again not a significant case. So what we are going to discuss over here is a system with under damping. That means there will be oscillations. So lower the damping is more oscillations over here. So we will be discussing only the under damped system over here. Now, let me write the first equation, which is equals to mu double dot plus cu dot plus ku is equals to f naught sine omega bar t. So that we can do some mathematics over here. This is our equation number 1. We just recall this equation number 1. Let me do some mathematics over here. Let us divide this by m. So it will be u double dot plus c over m into u dot plus k over m u, that will be equals to f naught over m into sine of omega bar t. Now from these equations we know that omega is equals to under root k over m. So omega square will be equals to k over m. So this can be replaced by k over m. And from this equation we know that c will be equals to xc times cr. Since cr is equals to 2 under root k over m, so a little mathematics will give me c is equals to 2 times m into omega into xc. A little mathematics can do that. No need to repeat this one. So if I substitute these values over here, what I will get, u double dot plus c is 2 times m omega into c divided by m u dot plus k over m is omega square times u is equals to f naught over m times sine omega bar t. So I can cancel m and m over here. Now what I can do, I can rewrite this equation, that is u dot is equals, u dot plus 2 times omega into xc into u dot plus omega square into u, that will be equals to f naught over m sine omega bar t. So this is our, say, equation number 5. It should be 4 or 5. Yes, 5. Now we want to solve this problem, and as we know that the sorry, my mistake, I was going very fast. In these two particular solutions, that means the complementary solution and the particular solution. The complementary solution is also known as transient state, and particular solution is also called steady state. Since these are under damped system, so after some time when there is an external force acting, so that will not have a significant impact on the overall performance of the system, but the particular solution, that is very important. So let us deal with this system. Let me rewrite this equation again and let us do some mathematics on it. That means u of pt is equals to c1 sine omega bar t plus c2 cos omega bar t. Let us do some mathematics and let us try to solve this problem. So the particular solution upt, this was equals to c1 cos omega bar t plus c2 sine omega bar t, where c1 and c2, they are the constant of integration, and our main problem is to find these constant of equations. What we can do? Now we can differentiate this equation 2 times. So let us differentiate this. First derivative u pt dash, this will be equals to c1, derivative of cos is sine, so it will be equals to sine omega bar t, and of course multiplied by omega bar over here, and derivative of sine is minus cos, so it will be equals to minus c2 into omega bar cos omega bar t. Oh, one mistake we did. The first term is sine and the second term is cos. We did a mistake over here. That was my mistake. C1 into, it was sine omega bar t plus C2 cos omega bar t. Now if we differentiate, derivative of sine is cos, so this will be equals to C1 omega bar cos omega bar t plus, instead of C2, now it will be minus, because derivative of cos is minus sine with a negative sign. So this will be minus C2 omega bar, derivative of cos is sine omega bar t. Now its second derivative, u double dot p t, that will be equals to, now derivative of cos is minus sign, so there will be a negative sign, C1 omega bar square into sine omega bar t minus C2 omega bar square, derivative of sine is cos, so it will be cos omega bar t. Now what we can do, we can substitute these three equations in equation number 5. Substitute in equation number 5. So what will be the result? U double dot, we can replace this with this one, that is minus C1 into omega bar square sine omega bar t minus C2 omega bar square into cos omega bar t. This is our u plus 2 times omega xc, and u dot is C1 omega bar cos omega bar t minus C2 omega bar sine omega bar t plus omega square into u, and u is C1 sine omega bar t plus C2 cos omega bar t, and this whole thing is equal to f naught over m into sine omega bar t. Now what we can do? Now we can compare the coefficients. How? It's a very big equation, so let us try to compare the coefficients. Like for example, here we have sine omega bar. Where else we can see sine omega bar? Sine omega bar, sine omega bar, sine omega bar. So we can compare the coefficients. That means minus C1 omega bar square, right? Minus C2 omega plus omega square into C1 is equal to F naught over M. So this is our equation number 6. That is the coefficients of sine omega bar t. Similarly, we can compare the coefficients of cos. So our first, let us identify what are the terms over here. So this is the cos, cos, and here one mistake, 2 omega into psi, it should be multiplied over here, multiplied by 2 omega psi. That was a mistake. Let me rewrite carefully. C1 omega square minus C2 into 2 psi omega into omega bar plus omega square into C1, and that should be equals to F naught upon M. So actually this is our equation number 6. Now we compare the coefficients for cos. So first of all, it will be minus C2 into omega bar square, then minus C2 omega bar plus no, here C1 it should be. So it will be C1 into omega bar into 2 times omega xc, and then the last term is plus C2 time omega square, and that is nothing but equal to 0. So these are the coefficients for cos, and coefficients for sine we have segregated. And now let us try to solve for C1 and C2. C1 and C2. What should be the easiest way to solve C1 and C2? Of course, we can use equation number 7, and let us do some mathematics. Now we can do some mathematics over here. We can recall our equation number 6 and we can do some mathematics over here. We can say divide equation number 6 by omega square. So what we will get over here, minus C1 times omega bar over omega whole square minus C2 into 2 times xc into it will be omega bar over omega because 1 omega will cancel and plus omega square will cancel, so only C1, and this will be equals to F naught over m times omega square. And we know that the frequency ratio R was omega bar over omega. So if we substitute this value, what we will get? We will get minus C1 times R square minus C2 times 2 xc into R plus C1 is equals to F naught divided by m. Omega square is nothing but k over m. So m and m will cancel out. So what we will get, therefore, minus C1 R square minus C2 into 2 times xc R plus C1, this will be equals to F naught over K. Further, we can combine these two. So if we take C1 common, it will be 1 minus R square minus 2 times xc R times C2, this will be equals to F naught over K. Let this be our equation number 8. Now we can recall our another equation which we developed by comparing the cos omega bar t. So if we recalling the equation, that was minus C2 into omega bar square plus 2 into omega into xc into omega bar times C1 plus omega square C2, that was equal to 0. Now we can do some mathematics over here. That will be equals to minus C2 omega bar square plus 2 times omega into xc. Now omega bar is nothing but equals to R into omega, then multiplied by C1 plus omega square C2 that equals to 0. So from here we can say that will be equals to minus C2 omega bar square plus 2 XCR into omega square times C1 plus omega square C2 is equals to 0. Now we can divide by omega square. We can divide this equation by omega square. What we will get? It will be minus C2 into omega bar over omega, that is whole square, plus 2 times XC into R times C1 plus C2, that will be equal to 0. Now omega bar over omega is nothing but equals to R. R is equals to omega bar over omega. So we can write minus C2 into R square plus 2 times XCR into C1 plus C2 equals to 0. So now our equation reduces to minus C2 into R square plus 2 XCR into C1 plus C2 equals to 0. We can take C2 common. So if C2 is common, then it will be 1 minus R square plus 2 XCR C1. This will be equals to 0. Before the equation number was 8. So this will be our equation number 9. And now we can play with these two equations to solve for C1 and C2. So from here, let C1 is equal to minus C2 into 1 minus R square over 2 XCR, and we can substitute in our equation number 8. So what we will get for C1 is minus C2 times 1 minus R square over 2 CR minus 2 XCR C2 is equals to F naught over K. So let us solve for C2. Minus C2 is common, 1 minus R square over 2 XC into R plus 2 XCR, and that is equals to F naught over K. So now we can say, let us solve over here. 2 XCR So it will be 1 minus r square. Sorry, I forgot 1 minus r square is also there. So here 1 minus r square whole square. So it will be 1 minus r square whole square plus 2 times xcr whole square, and this is multiplied by c2 with a negative sign. This equals to f naught over k. So we can further reduce it. So we can write that f naught over k, of course with a negative sign, is multiplied by 2 xcr over 1 minus r whole square plus 2 times xcr whole square, and this is equals to c2. So we can now use this value of c2. This is our equation number 10. So from equation number 10 we can substitute back into our equation number 9, and we can get the value of c1. So substitute c2 from equation number 10 into equation number 9. So our equation number 9 was c1 is equals to c2. We can use this equation instead of 9, right? Okay, so we can write that c1 will be equals to minus, then instead of c2 we can write minus, so it will be plus f naught over k into 2 xcr over 1 minus r square whole square plus 2 xcr whole square, and then is equals to 1 minus r square divided by 2 times xcr. So that means we can cancel 2 times xcr. So the value of c1, now we can write c1, this will be equals to f naught over k into 1 minus r square over 1 plus, sorry, this is minus one minus r square whole square plus 2 xcr whole square. So this is our equation number 11, if I am not wrong. Yeah. So this is the value of C1. Now what we can do, we can substitute these values back in our final equation and we can get the result. As you know, if you recall, our final solution was e raised to power minus xc omega t into a cos omega dt plus b sin omega dt. This was our complementary solution, and now plus C1 sin omega bar t. So C1 is f naught over k into 1 minus r square over 1 minus r square whole square plus 2 xc r whole square, and this was multiplied by sine of omega bar t, and plus C2, so here it will be negative, f naught over k multiplied by two xc r over 1 minus r square whole square plus 2 xc r whole square, and this was multiplied by cos omega bar t. So this is our final solution of the equation number 1. Now, this is a very, very interesting solution. Why this is an interesting solution? Okay, that's a very good question. We know the formula that sine alpha plus beta or sine alpha minus beta sorry. We know that sine alpha plus or minus beta is equals to sine alpha into cos beta plus minus cos alpha into sine beta. Can we see any resemblance of this formula somewhere here? Can we apply this equation? I think so. If this term comes out to be like a cos and this like a sine. That means if I can draw a triangle, let it be theta. So what will be the result? Say 1 minus r square is the base and 2 xcr is the perpendicular. So of course this hypotenuse will be this hypotenuse will be 1 minus r square whole square plus 2 times xc omega r whole square under the root. So from this figure I can say that cos of theta, this will be equals to 1 minus r square over 1 minus r square whole square plus 2 times xi r whole square under the root. Similarly, I can say sine of theta, this will be equals to 2 times xi r over 1 minus r square whole square plus 2 times xi r whole square under the root. And of course tangent theta, this will be equals to 2 times xc r over 1 minus r square. So now I can say that this is cos of theta and this function is sine of theta, but I have to take something common. What? Let me do some mathematical trick over here. So my equation u of t is equals to e raised to power minus xc into omega t into a cos omega dt plus b sine omega dt. Up to here this is okay, but then I can take plus f naught over k common, and I can take 1 minus r square whole square plus 2 xcr whole square under the root. Then what I will be left with, this will be 1 minus r square divided by under root 1 minus r square whole square plus 2 times xcr whole square under the root into sine omega bar chi minus 2 times c into r over 1 minus r square whole square plus, of course, 2 times xcr whole square under the root and cos omega bar t. Now I can apply this equation. So this is cos and this is sine. So now I can write that u of t, this will be equals to e raised to power minus omega minus xc omega t into a cos omega dt plus b sine omega dt plus f naught over k divided by under root 1 minus r square, of course, whole square plus 2 xcr whole square, and this is multiplied by this function, so this will be reduced to sine omega bar t minus theta. This is our equation number 12. So now we have reduced to our final equation, which is equation number 12, where we know that this is our complementary solution. And this is our particular solution. And this complementary solution, it represents the transient response, and as we have discussed before, that transient response dies out with the passage of time. And this dies out eventually, this transient solution, it dies out as e raised to power minus xc omega t. This becomes almost nearly equal to 0 when this approaches to 0. So eventually this complementary solution will vanish. What we will be left with, we will be left with our particular solution, which is called the steady state solution. So if we write our particular solution like this is our particular solution, this is equals to f naught over k over 1 minus r square whole square plus 2 times xcr whole square, of course, under the root into sine omega bar t minus theta. So this particular solution has a constant term like this, and this term is called amplitude. And this amplitude sometimes is shown as u or p. Let us show this with the sign p. So we can say our amplitude P will be equals to F naught over K divided by under root 1 minus R square whole square plus 2 times XCR whole square. So this is our amplitude of the steady state motion. Say this is our equation number 14. So far we have solved our problem. I can conclude like this, that if there is a harmonic force acting on a damped system, then its transients, which depends on the damping of the system, will die out gradually as the factor e raised to power minus xc omega t dies out or becomes very low, but the steady state solution will prevail, it will be there, and its amplitude will be given by this equation. So I think I should conclude my lecture over here. Thank you very much. In my second lecture, I will try to solve the same equation with a different approach, and hopefully we will discuss more aspects over there. So for that time, let's wait for that time, and for the time being, this is the end of my lecture. Please do not forget to subscribe my channel, and always I am waiting for your comments. If you have any comments, any question, you are always welcome. So thank you very much, and bye.